Hi, I'm Brian Mullin, and this is Balls Out Physics, episode 5.1, Propulsion in a Vacuum Chamber. Now, in the last episode, in episode 5, I stated that space sucks, and a lot of people said that that's not true. And I made this video to kind of explain why I think that is true, or would be true if it exists as we've been taught, and why it would be different from a vacuum chamber that we would construct on Earth. And so I started working or thinking about how a vacuum container would be constructed, and thankfully somebody had already messaged me about some experiments he had been doing on his own with CO2 cartridges. So I have to say thank you, Rob, for giving me this idea. But I thought about a CO2 cartridge, and the CO2 cartridge somehow suspended in a chamber, in a vacuum chamber like this. I've got the CO2 cartridge, as you can see I traced it, suspended from a string, and the idea would be that we suspend it from a string because we have to deal with weight on Earth, and we'd rig up something, which is this little green line here, some kind of pin that would rotate and puncture the end of the CO2 cartridge. Okay, and that would spray the contents of the CO2 cartridge out, and we'd be able to test whether it works or not. But thinking about how a CO2 cartridge works, right now in this CO2 cartridge there is compressed carbon dioxide, and the carbon dioxide, the compressed gas, is pushing on the inside of the container, kind of like I showed in the last video with the compressed oxygen. Okay, but at the same time, the air pressure, the 14.7 psi that I also pointed out was considered atmospheric pressure, is pushing back on the container. So the net difference between the CO2 pushing on the inside of the container and the atmospheric pressure, or the air pressure pushing on the outside of the container, is how you determine what force is on the actual container. And then the container has to be strong enough to resist that force, or it would rupture. And so, since if you puncture the end of this CO2 cartridge, all the CO2 is going to come flying out. If you had it in your finger, that would want to shoot out of your fingers, right? And I believe that's because, yes, the thrust is creating a reaction on the CO2 cartridge and pushing it, but also the CO2 is pushing against the air, and the air is pushing back. Okay? Whereas in a vacuum, I don't think you would have that. But then you've also got the vacuum chamber to construct, and that is basically done in the exact opposite way. Okay, so you have this vacuum chamber that I just drew as a big box here. I actually got this idea from watching something Mythbusters did, and you'd have to have a pump on it to suck all the air out. Now, to visualize how that would work in reverse, you can just use a bottle. Okay, and no jokes about this, but when you go to suck the air out of the bottle, you're sucking the air out, which is pulling on the inside of the walls, and the atmospheric pressure is also pushing on the outer wall. So when you suck, it collapses, right? So you have to build this chamber to be strong enough to resist that outside pressure pushing on the walls. Excuse me, actually, I think all the force is from the outside pressure pushing in. When you try to suck it in, that's when you really experience the air, the weight of the air, or the pressure of the air on the outside of the container, because you're pulling the pressure out from the inside, creating the pressure differential. All right, and so this is why I think that space sucks, because space doesn't have a container. As it's theorized, our universe, as we've been taught, is supposed to be expanding infinitely. It never stops expanding. So space always has more space to expand into. So any propulsion that's sprayed out into space is just going to expand infinitely with the rest of space. There's no way for pressure to develop. See what I'm saying? And so to create this vacuum chamber, the first thing you would do before you run the experiment is turn on the pump to suck all the air out. Okay, so all the air in the container gets sucked out. Okay, now the air rushing past the CO2 cartridge, which would, if we're hanging it from a string like I have here, would probably get it moving, rocking back and forth. So after all of the air is sucked out of the vacuum chamber, and assuming these walls are strong enough to resist the the air pressure that is pushing on it from the outside, then we now have a vacuum, or a vacuum chamber, with zero pressure, not negative pressure, or like I said in episode 5, or that, you know, or that not a constant sucking pressure. Once the pump kicks off and you don't have any stuff or any air left inside the vacuum chamber, then you just have this positive pressure pushing on the wall, and the pressure in here is essentially zero. Okay, so if you were to puncture the side of the tank, the pressure differential would make since there's zero pressure in here, now here the pressure is, P ATM equals 14.7 psi. Since you have that pressure out there, all the air is going to want to rush into the vacuum chamber. Okay, so suck all the air out. All right, turn the pump on, suck all the air out. Okay, CO2 cartridge stops swinging. This is just one idea. There's probably better ways to support this, or other ways to support it, because this does create a problem, which I'll show in a second. But okay, air's out of it. There's zero pressure inside the tank. Use this blue marker for pressure. Dropped my bottle over there. So P ATM or PC for chamber equals 0. Right now. Okay, so we've got this little pin rigged up somehow. Either if it's activated wirelessly, that would be a good test to see if electromagnetic waves can pass through the wall of the container and continue passing through the vacuum, or maybe we have some kind of wire hooked up to this string to activate it through a wired connection. So this little pin flings down and punctures the CO2 cartridge, and then bounces back out of the way. We designed it to do something, and then immediately this high energy CO2 sprays out because you have so much pressure inside of the cartridge. Now the pump's off, but this is sealed. Immediately this chamber begins to pressurize, because remember, there was no air in it before, so now this is no longer the case. Immediately pressure builds in the chamber from the propellant. So now basically what's happening is the CO2 expands out and bounces off of the walls, and then creates the reaction that we need to push on this CO2 cartridge. So in my opinion, building a vacuum chamber on Earth isn't the same thing. I don't think we can build a vacuum chamber on Earth that would simulate what outer space is supposed to be, as we've been taught. But I did think about it a little more, and I said, okay, well, could we do this? In order to simulate space, infinitely expanding away from itself, or the universe infinitely expanding away, what we could do is have this pump timed or linked to this pin, so that at the moment that this pin strikes the CO2, this pump comes on and evacuates or sucks out the propellant at the same rate at which it comes out of the CO2 cartridge. We could figure out how fast and how much CO2 comes out in a set amount of time. And so the pump kicks on right when this pin hits, and so the propellant sprays out, and then of course gets sucked right out by the pump, right? And then gets sprayed out into the air or the surrounding environment. And that, in my opinion, would somewhat simulate what we've been taught outer space is. But that, in my opinion, would make it so this won't move. Now, theoretically it wouldn't move. I mean, this would have to be timed perfectly to simulate outer space. And so, assuming this doesn't move, I mean, it might get pulled a little bit. I mean, there's a lot happening, and we have to assume that the pump can suck all of that CO2 out. And you kind of see where I'm going with this, where we're eliminating the ability to create a reaction. But that's what we would have to do to simulate space, in my opinion, just after really thinking about this. But the other problem here is, once this, if you do gain some thrust, say we don't have the pump on, this string, once it moves here, once the It's a terrible CO2 cartridge drawing, but you see what I'm saying? Once it moves up here, now we have weight pulling down against the thrust. So a string might not be the best way to do this. There might be better ways, but that's the other problem. On Earth, we have to deal with weight, whereas in space, as it's theorized, it's weightless, so we don't have that problem. Okay? So this is why I say space sucks, because it does not have a container. Okay? So another thing I was thinking about, though, is just to go back to the action-reaction. If you've got this set up to do this and it works and you get no movement in here as we should expect, okay, based on action-reaction, now you have a force, you have this propellant being ejected from this pump, which is pushing on the container. So just to keep, stay in the spirit of Newton's third law and action-reaction, now there's a force pushing on this pump. You know, this force is pushing this way, so you get a reaction this way, and then that in turn is pushing on the vacuum chamber. Now, chances are that force isn't going to be very large, and the weight of the container is enough to create friction between the ground, which I have here by these dashed lines. This is typically how we sketch ground in structural engineering. You'll have the weight of the container multiplied by a friction coefficient will give you a resulting force of friction here, which will resist that force and keep it from moving. Okay, so just keep that in mind. So this is why I don't think we can even really, I mean, this would be so hard to time and do, and we're essentially defeating the purpose of the propellant by sucking it out as it's sprayed out of the CO2 cartridge. But the point of doing this episode is to show that when the CO2 leaves the cartridge in space, or what it would be compressed oxygen, but this is a pretty good representation of how those little jets work. When the oxygen is sprayed out into space, it just expands with space. There's nothing to push back. Whereas if you didn't have this pump on, as I've got shown here, you don't have the pump on, then the container fills with the CO2 propellant, and it becomes pressurized again, and so that would affect this. It would create a reaction, and you would probably see the CO2 cartridge move. So just wanted to go over that real quick and explain why I said space sucks and why it wouldn't suck in a container unless we had the pump turned on. So thought I'd make this short video, and to continue thinking about the action-reaction process, I'm planning to do another sub-video, 5.2, in which I want to use a spring in lieu of the compressed gas to simplify things, and to show why I don't think conservation of momentum would work, or using that principle would show that the gas could propel the spacecraft, because it's really based on, I mean, the conservation of momentum is really based on Newton's third law. So until next time, we'll keep looking at this problem and get into some different stuff with episode 6. So see you then. Peace.